Place the silicon wafer into the beaker. Add sulfuric acid and hydrogen peroxide, 2:1, to the beaker. Wait 15 minutes. Close the workbench window. Pour the solution into the designated beaker, taking care to prevent the wafer from falling. Rinse with deep water. Ultrasonic cleaning for 15 to 20 seconds. After taking out the wafer, clean it with deep water again. Repeat 4 times. Use an air gun to dry the wafer and save it. Finally, pour the used piranha solution into the waste bucket. After cleaning, use the furnace to make an oxidation layer. Deposit at 1000 degrees centigrade for 40 minutes. The final thickness is 300 nm. Here we are going to use the film mask. So we need to clean the old masks by piranha cleaning and CR etching. After cleaning, use a tab to attach the film masks onto the glass substrate. Sample loading. Use a dropper to add an appropriate amount of AZTX of photoresist. Remove the sample. Soft bake at 90 degrees centigrade for 90 s. After cooling, conduct the exposure using mask liner. Since the open window is the first pattern, we don't need to align the marks. Just make sure the pattern on the wafer area. Exposure for ERS. Post-exposure bake at 110 degrees centigrade for 90 s. After cooling, develop in AZ300 developer for 50 s. Rinse by dewater and dry. Assemble the wafer into the jig for TMAH etching. Add some water into the holding box. And use the air gun to remove the bubbles on the surface of wafer. Turn on the hot plate in advance and wait for the temperature rise to 80 degrees centigrade. Remove the copper tube and cover and put in the prepared sample. Bubbles will be generated during etching. The etching rate is 0.5 micrometers, mean our expected thickness is 40 micrometers. After etching for 80 minutes, take out the sample. Check the thickness using surface profile. Conduct the second oxidation. Same operation as the first oxidation process. To make the sensor layer, we are going to deposit a CR layer by spatter. Set the power to 50 W and deposit for 1 hour. The expected thickness is 200 nanometers. Before starting deposition, a period of pre-sputtering is performed to remove the oxide layer of the metal. Patterning the sensor using photolithography. Patterning with chromium etching to obtain metal sensors. Here we need to coat PR on both sides of the wafer to protect the oxide layer. In order to ensure complete coverage of the pattern, a lower speed 2000 revolutions per minute is recommended. Remove the sample. Soft bake at 90 degrees centigrade for 90 S. Now need exposure for the top side. After cooling, bake at 110 degrees centigrade for 90 S. Spin coat at the back side using the same method. Soft bake at 90 degrees centigrade for 90 S. Backside alignment with infrared light for exposure. After the back pattern is made, bow etching is performed to remove the oxide layer. Then perform back TMAH etching. The operation method is the same as open window etching. Place the assembled sample into a TMAH solution at 80 degrees centigrade. Try to keep the sample vertical for uniform etching. Bubbles will be generated during etching. Take out the sample halfway through the etching process to check the thickness and change the etching direction. When etching is almost finished, try to ensure that someone is watching the etching progress. Finally, the actual thickness of the etching is measured using the surface profile. After production is completed, a 3D printer is used to make a fixture and assemble it on the sample. Build an RF wireless transmission system using Arduino kit. The wireless transmission and real-time plotting capabilities of the system are tested using a Wheatstone bridge built with 4 commercial resistors. Here is the final wireless system and pressure sensor test setup. When we apply different air pressures with a syringe pump, we can see the output voltage change of the Wheatstone bridge circuit in real time through the wireless system.